try to get the charade over with. As it is, I don't have your homeworks. What happened was the TA, she needs a little extra time because her PhD exam is coming up real soon, so she's pretty stressed about it. So like I told her to take a little extra time. She has to make a miniature presentation today. So I'll have your homeworks on Friday. Remember, you have the answer keys. You can already pretty much figure out how you did. So sorry about that. But then Friday I'll have them, so don't worry. Of course, I'll have the answer key up on this guy as soon as I turn back. Well, at 5 o'clock, so you have till 5 to turn in your homework as normal. Problem set again. Everyone can recognize your voices. I actually do. So as normal, I have not written your problem set yet. I'll do that tonight. It will be up later tonight, around 9 or 10, like every other problem set. So, if some of you may have seen, it looks like I made a bit of a screw up on problem 3. The answer is still valid. The answer is that question 3. I sent an email, so if you're still working on it, it doesn't matter. Question 3, each reaction actually ended up being equal to the other reaction in delta G, so there was no clear dominant reaction. But what I screwed up was I had the electron on the wrong side for reaction A, and if that was the case, then the battery would be 0 volts. Instead, the way I designed it, it could be 3 volts. So, because when you switched A, the electrons were on different sides of the arrow, and then that works. That's a real battery. So basically, as long as you didn't say anything stupid on number 3, we're going to count it right. So sorry about that. That's, I write the equations. The question's fresh every semester. And as I mentioned to you last time when I was teaching about that freaking grant, last semester I made a mistake like that, except worse on every homework, because I was working on that grant for 6 weeks. And so actually, this semester I'm proud of myself, yay, because I actually made less mistakes in your homework than any other semester I've ever done. So, yay. You don't care. So hopefully, thanks. So hopefully I won't make any more mistakes. And God forbid, I always have the test double check in case I do something like that on a test, which case, like I say, it gets spiraling. It was a little annoying, right? So I know that question on a test, the answer was still legitimate, but it would be confusing because you could still build a good battery out of it. Let's see, then Friday. Now, normally we double lecture on before a test, so obviously not this Friday. Next Friday next, is that your test, or is it one after that? So
2 weeks from this Friday.
2 weeks from this Friday, okay. So anyway, all right, when it comes to double lecturing, I'm not going to do it. I'm still going to cover 346 stuff. We're going to do distributions. I'll have a full lecture prepared. I just was a little short last time because I really covered all the material. Really by the end of next week, you could take a PChem 1 class anywhere and you would get as much or actually less material that I've already covered. So in terms of what should you have gotten for PChem 1 by next week, I've done it. So if you, when I update the calendar, when I go back, I haven't updated it yet. I don't know what I'm going to do for the last 2 lectures. I'm not going to cancel. I'm not going to do that because you paid me not to. I may do some special topics because actually everything you've learned, sorry about this folks, I know it sucks, but everything you learned was known up until about 1890. So I've gotten you almost a whole century behind in terms of your knowledge. And it's just how it is, I mean, you have to learn from the bottom, and the bottom always gets more bottomy as time goes on. So since I'm a research active faculty, what I may try to do is find 2 lectures on something, I don't know, younger than 1890, like something modern actually about PChem, and so I might actually do that, lecture on that. And I may or may not have them on the test, but just understand if you look at the calendar, I've changed the calendar, and I have 2 days blank, not canceling class, I just don't know what I'm going to talk about. So, and I think that would be kind of nice to actually have something a little bit younger than 1890 in this class. And when you do 346, you'll go up to 1930. And then that's about it. So, anyway, any of you have any questions? We're okay? Everything seems okay? Right, so folks, and again, this is all going to be very easy from here on out. Remember, 346 is not going to be fun, but I'm going to help you go over that. And look, almost everyone passes 346. It's relatively unheard of not to pass. And even when I taught this class back when I did PChem 1 and 2 with the same class, I did that 2 years ago, I was shocked at how much better people did with harder material. And so I'm not worried about it at all. We're going to be fine in that class. But equations do go across the board, and they do that quite often. Okay, if no one has any questions, then let's get into this horrifically boring material. One component phase diagram. All right, what am I going to ask? I may just give you a P versus T little thing with nothing in it and say fill it out. That would be a pretty reasonable question. Triple point, high pressure, low temperature solid. Low pressure, high temperature gas, meaning that liquid. This is critical. Only one triple point. Other triple points can be in the solid region. There's like 10, we talked about allotropes, like how many different forms of solid water is there, ice. I believe there's like 10 crystal structures of ice. And what's really cool, when I was giving an invited lecture at Notre Dame, a theoretician does molecular dynamics, which is just molecules moving around according to mass times acceleration. It's just you turn little water molecules into little cars, so they move according to Newton's laws. This guy accidentally had his water molecules form a new phase of ice that has never been experimentally observed. So now everyone is looking for it. So it's one of the few examples of a theoretical prediction that has not been seen experimentally. So anyway, lots and lots of triple points up here. What much to say about that? Then we did Gibbs phase rule, which is, we're going to do some really kind of weird things today that are kind of hard, but hopefully I can walk you through them. And they're connected to getting to understand this a little bit better. I know it's kind of shake and bake, but what we did was, the whole thing came about by saying, how many things can I control? And those were the sum of all the intensive variables: mole fractions, temperature, pressure, and chemical potentials. Those are things I can control in various ways. And we added them up, but that's not right. It's not right, because when it came to mole fractions, if I say, and that would be the C part, if I say, well, I've got water and ethanol, so therefore I've got 2 mole fractions, no, you've only got 1, right? Because 1 is 1 times the mole fraction of the other. So you set 1, you set the other. So a singular mole fraction, again, that's one thing, controlled 2 things. So we overcounted. And that was really easy to see. So we figured out how many equal signs there were. When I wrote down all the mole fractions have to equal 1, we counted the number of equal signs and we subtracted that off. And then we did the same for chemical potentials and subtracted those off, and that's what we were left with. All right, now I think it's really, really easy to see that you can't just, in the original form we had, I think we started with 2 plus C times P, that was mole fractions. It's really easy to see that, yeah, you obviously overcounted mole fractions. It's just plainly obvious. The chemical potential one, why did I subtract that out? I mean, I totally get the mole fraction one. That's really simple. But the chemical potential one may have been like, well, wait a minute, why does that get removed out? Other than the fact that it's just there were a bunch of equal signs. Well, what about that meant that you had to subtract it off? We're going to cover that today. And then also remember our Gibbs phase rule. F is traditionally called the degrees of freedom, just, that's what they call it. Remember, a number of chemically independent components per phase, and that's temperature and pressure. It's showing up as the number 2. Okay, so now let me write this down. What we're going to do is we're going to work this guy in a box where things are reacting. Right, so this is going to help us understand what happens when things are reacting in a box and what you can control, the number of things you can control. And it's also going to help you understand that chemical potential bit, I think quite a bit. Why did that have to get subtracted out? All right, but I have to define some things, so I'm going to write out some stuff and kind of gamble a little bit at the same time. And right now I'm going to define constituent. I hate this stuff because the words are just long. A constituent is everything in the pot. In the pot. Okay, so this is not C. The C is the components. Now, it sounds like the components should be the same thing as the constituents, meaning that, literally everything I throw into a pot, water, ethanol, ice, yada, yada, yada. Those are all constituents, but components are generally, especially when there's like a chemical reaction going on, those will almost never be the same as the number of constituents. And the components is, let's see, okay. It takes a long time to write this out, but I have to write this out. I hate writing this. It's the smallest number number of smallest number of chemically independent species. Chemically independent species per phase. I hate just writing things out in silence, but here we go. But you really got to know that you should be writing, okay? So in case that's not clear. And then this is C in C minus P plus 2. Okay, a damn long-worded thing. So let me give an example. I'm going to give a bunch of examples as usual. This is just the best way to get this across. Normally I don't like doing that, but that's for homework. But two things, you'll get this part, and again this is C, and you'll get the whole chemical potential bit when it comes to why that was subtracted out. So we'll go ahead and start giving examples. Okay, and again, what number of things can I control when a reaction's occurring in a box? And I'm going to have solids and liquids and gases, and let's do one of my favorites. Let's talk about ammonia production, and I need to make sure this is in equilibrium. Into gas, H2 gas. Okay. Okay, now again, the point of this game, and a couple of homeworks, maybe one on the test, is to get C and to get phase ruler. Okay, just like electrochem, I know it's floundering badly when I talked about it, so it's on Friday. I know it's floundering badly, I didn't get them right. But like that, I have a formula. There's a little notation for you to get this right as well as possible. These are kind of like little word game puzzles, though. Okay, so now I'm looking at this thing. It says per phase. We'll be chemically independent in a minute. So what I do is I write phase down, and then I write constituent. So, sorry, shorthand. All right, constituent, and I'm going to figure out the number of chemically independent constituents per phase, then I add them up to get the total number of components, which you see in that. Okay, so, sorry, gas. That is, I never get this right, okay. So I've only got one gas phase. Now what's going to come up later in another example is that, like, if I have a solid and gases, then I'd have a solid and a gas phase, which is nice because the solid phase has one constituent, so it's just easier. But we're doing gas phase. Okay, so that's the phase part. Now we've got to do the smallest number of chemically independents. Again, the best way is through example. I see three things, I want to write 3. Anyone want to guess what the real number is? It's not 3. 2. 2. Or 1. It's 1. And now I don't really have to say which one it is, but it's easy to say that that constituent is ammonia itself. Maybe this yeah, it's chemistry, right? It's easy just to say it's this one. It doesn't have to actually, it doesn't really have to be that way. Okay, but now here's how this works. It's easy to think of ammonia as the one constituent, the one component actually. Now that I've written out all the phases, there's only one component, is ammonia. It's the chemical independence. This guy came from here. This one thing came from there. Right, so the smallest number of chemically independent species is either 2 or 1. The smallest number is 1. Right, now, so that's one way to think about it. All the atoms in these two things came from this one thing, and 1 is less than 2. Let's see, there's other ways to think about this. Yeah, okay. You could say to me, but what happened was I had a box and I filled it with nitrogen and hydrogen. I started with those 2, I added 2 things. Okay, it's still 1. Why? Because there's actually only one equilibrium constant. Right, that gives me all 3 species. So that's the one thing, that's the one component. That's why I have only 1 degree of freedom, because I only have one equilibrium constant, and we know how to set up equilibrium constants, and then I can figure out what the concentration of everything is from that one thing. And the control could be, I guess, I'm not quite sure about this, I guess control could be that I can change this reaction into something else that has a different K constant, right? And so that's my control. So two things again, these atoms came from this one thing, and even if you think, well, it's two because I can just add these two, and that's the control I have, but you only have one equilibrium constant, and so that one thing decided how these two things that you added would turn into this one thing. So two ways to think about that, and that is correct. Okay, more practice. Okay, now this is a good one. Now I'm going to start doing the phase thing. All right, so that's solid ammonium chloride, often in industrial cleaners. You can buy this stuff pretty easily. Kind of sucky because it's easy to make a bomb out of. Okay, it decomposes into ammonia gas and HCl gas. Okay, again, the name of the game is to get C. We're going to write phase and constituents, add them up to get the number of components, which is C. Now, what I like about this is that you have one thing in the solid phase. All right, so that one's easy. We're done. All right, but now we've got gas phase. Obviously, the answer is 2 or 1. So either we're going to have 2 components or 3. You get it wrong, you lost a lot of points. Okay, 2 or 1. 2, because there are 2, and they don't contain the same number of atoms. Now let's hear from someone else. Who gives me a different number? It should be correct.
1.
1. How did you know? It's 1. If I have a mole of this, how much of that do I have? 1. That's right. Yeah, you see, it's another. There's lots of levels to this. Now, again, the way we're going to build this box, we're going to make it sensible. I'm going to take a box that's under vacuum, and I'm going to shovel this in, and it's going to decompose to a certain extent, not all the way, because the box is small. And it's true that if I have 1 mole of that, I automatically have a mole of that. Yep, there you go. So this is the V1, so therefore C. The phase rule is 2. And let's also do the calculation. I should have done it over here, just so you, sorry, I should have done this before. 1 minus 1 plus 2 is 2. And basically that means you can still control temperature and pressure. And you may change this equilibrium, but you'll still have all of it there. And let's see, 2 minus 2 plus 2 is still 2. Still the same idea. You can basically still control, you can mess with temperature and pressure and still keep your solids and gases. You may shift the equilibrium, but they're still there. That's what's important. Okay, and so again, there's a little bit of trickery to this. And then, how do I want to explain this? Oh yeah, one other thing is, I guess you can imagine if you had 3 phases. Let's say you had liquid ammonia, then this guy would have gone down to 1, right? Right? No. Yes. If that was liquid, wouldn't I have 3 phases? Huh?
Not possible.
But you,
I would have 3 phases. So does this go down to 1?
no.
Why
Well,
not? Because I'm obviously tricking you. Is that the answer?
yep.
At least you had the guts to say it. What does that turn into? 3, right. I would have had a solid gas liquid phase. Okay, now, here's the thing. Why is this guy different than this guy? Okay, number of degrees of freedom is the same, whatever. But I have 1 component here, 2, and it's only because this one was a solid. So why can't you make the same argument that here, again, I can say that I have 1 equilibrium constant. I can certainly say that that's true here too. And I can control the equilibrium constant because maybe I'll change the chemicals around. That works. That's my degree of control. Well, I can do the same here too. But so where's the extra degree of freedom? Why does that solid suddenly kick in something more? Right? That didn't occur here when I can make the same argument that all I need to know is the equilibrium constant. Because that's not right. And let me remind you, this is correct. As you see, you're probably kind of, I think you're all annoyed with me, and I'm asking questions from test 1 and test 2. That's me forcing you to study. And remember, this problem set is probably going to be the last one, because I don't know that I have time to grade 11 problem set. But to go back and to answer that question, they both work. I need to think about chemical potentials. Right now, remember that this stuff, this solid, will dissociate until the vapors of HCl and NH3 are in chemical equilibrium with the solid. Then everything stops. Right now. Now, I'm not going to do this experiment in an open container. Why? What would happen? Right, it's like water evaporating. It all goes away. So I'm going to put it in a metal container, right? That's going to make this measurement meaningful. This measurement of equal chemical potentials. Okay, now, how do I want to define U then? A G per mole? Yeah. Okay, we're going to be at constant temperature in a metal box. That's constant volume. Do I want to be working with G then? A. I want to work with A, right? A is a function of temperature and volume, not temperature and pressure. Now, again, temperature and pressure is always much more useful, but in this case, to make this meaningful, I have to do this in a metal box. So I'm at constant volume, and I want to take a chemical potential naturally as a function of A. Now, I can still do it in the form of G, but generally, you might find that it's just harder to work with it that way. But so I'm going to stick with A. Okay, now therefore, the change in chemical potential is going to be the change in A. Now I'll keep N constant because I've got this stuff in the metal box. I don't know how it's going to be changing. And okay, I've got my temperature thing, and then I remember A is the one that's always everything is negative. Okay, I've got that. Now, let's do each individual, then what I want to do. Then I want to look at how so again in my picture here, to make this a perfect experiment, I'm going to put that solid in a box with at no pressure. It'll be a vacuum, and as the solid dissolves to gases, the pressure is going to rise. All right, as the pressure rises, the chemical potential of NH3 and HCl are going to start to rise, and eventually they'll rise to the point that they're equal to the chemical potential of the ammonium chloride. So I'm looking for a rise with respect to pressure. And, sorry, just trying to be as exact as possible. Now again, we're at constant temperature, and so so this term is gone. And actually, let me be sure I'm doing my notes right. Okay, so then this is going to be minus P over N, change in nRT over P, change in P. Okay, so the perfect gas law, whatever. P, RT, okay, you got minus sign over P squared. And that's equal to RT over P. And that's equal to V over N. Okay. Now, you may notice that I said constant T, constant V. I should have eliminated that term. But what I want to do is I want to talk about changing the size of the box. See, that's actually your other degree of control. That's why I did not set this to 0. What the point of this is that the chemical potential of those gases is going to increase as they are created. They increase pressure, they increase their chemical potential. I remember that when you have very little amount of material, the chemical potential is very low. Remember we talked about that when we did reactions? So I know that initially the ammonia and HCl have no chemical potential before they exist, because something that doesn't exist has no chemical potential. So that's very easy to understand. And as they create, they rise, and they rise proportional to the size of the box you put them in. Let's do this another way. You know this is going to be on the final. Let me solve for the change in chemical potential as a function of pressure. I'm going to go back here. And so if you integrate them, you've got delta change in chemical potential is RT ln PF over PI. Okay, so, right, now we can see lots of things here. Again, this is the rising the chemical potential of the gases, and I'm going to put it in a vacuum at first, so the final pressure will be finite. So the point being is that wherever it decides to, whatever the final pressure decides to be, is because the chemical potential rose as a result. So now you can see that if I did this in an open box, this would be 1. Right? If it's an open box, it starts at 1 atmosphere. I have my box, but it's open. I shovel my ammonia chloride in. And the thing is that because the wind blows the chemicals away, this is always 1. And that makes the chemical potential change 0. Now, if the chemical change is 0, then ammonia and HCl never rise to match the solid. They can't. They're always at a lower chemical potential. And then the wind blows them away, and that's why your solid will completely sublime. Technically, it'll sublime to nothing. You can see it right here, because he never gave those gases a chance to increase the chemical potential. That's why it went away. So, but anyway, that's a little factoid. My real point is that you picked up a degree of freedom because you got to choose what size box it was in. And it mattered, because that size of the box is going to change the final pressure, it's going to change the equilibrium, and you controlled it. So there you go. You got to choose what you put in the box, so that equilibrium thing still matters. I mean, there's still an equilibrium constant. But it was also a function of the size of the box it was in, which wasn't true before. So, there you go. That's kind of neat. And here's a little aside. Remember that dA, dN, a constant T and V is dG. Just in case you forgot, you had this on the homework. Remember that? Chemical potentials are equal. These are chemical potentials, and as long as you hold the natural variables constant, then the chemical potentials are all the same. Just real quick, let me do this. Okay, so let me do this guy. Change of G over M, minus S over M. Sorry. Okay, a constant T. This term goes away. This term turns to 1. I know I hold pressure constant, but 0 divided by 0 is still 1. Yeah, same thing, see? So just to remind you that there's actually, I never went over it then, but there's actually a lot of meaning to that. That I can actually work these chemical potential problems in any form I choose, as long as I'm careful about what I hold constant. And I will get the same answer. It just depends on how hard it takes, how long it takes the question.
The PI, I thought you said initially it was a vacuum. So how do you handle the PI?
Nothing, there's no such thing as a true vacuum. Right. The best humans, we can actually we can make vacuums better than the vacuum of space by a wide margin. I think space is 10 to the minus 10 torr. We can hit 10 to the minus 14 torr, I think. So it's something like that. So that's kind of neat, but no, there's never really such a thing as a true vacuum. So that's kind of a hand-wavy answer. Yeah, there's, if you go to grad school, right, and you'll learn that there are secret terms in here that I'm not expressing. There's actually, don't be writing this down, please. It turns out that in almost any physical equation, there's a plus an imaginary term that covers all kinds of really bizarre quantum mechanical stuff. It's really small, so it's not worth considering, especially in this class. But when it comes to the fact that that would technically be 0, and that would be a problem, that imaginary term actually wipes it out. So I don't know if that's real or if that's humans realizing that's a problem and tacking a term onto this that makes it go away, or maybe it is real. Because, just because if I ever could create a perfect vacuum, it sounds like this should explode, right? I should add something that's kabam, I'm dead, you know, the whole world is dead. That's anyway the answer there, so anyway. Any other questions? We're set? Okay, so anyway, I hope that made that a little bit more clear. Okay, let me give you a really hard example. Oh, don't forget this stuff, folks. You're final, it's nearly half a grade. And I try to do this more and more, constantly bringing up stuff we've done so that you don't forget. All right, let me give you a really freaking hard example. It's about the hardest one I could ever ask. I would not put one this hard on a test. And you know what, I'm going to post several examples. I have a little handout. I have a handout with several more examples. Because I actually will get these wrong myself sometimes, because this really, these are like brain teasers that kind of suck in all honesty. Okay, now let's do this one. Again, phase. And what do I say? Constituent component, I already got. Constituent. Constituent phase. Okay, sorry. Right, you gotta know what phase is. Okay, again, towards the gas, there's 1. So automatically I've got a C of 1. But now solid. Now, when it comes to these kinds of problems, it's kind of rare. All right, so I've either got 3 or 1. 3, 2, 1. All right, it's got to be one of those. It's really rare to set these up such that all 3 is the answer. You can almost always, not always, there are 1 or 2 examples where I have 3 solids and it turns out that there are 3 constituents add to the components, but that's rare. You can almost always shave off 1. So I'm pretty sure it's either going to be 1 or 2. 2? Now, hold on a second. I've got 1. This isn't here. I almost got myself confused. I've got 1 solid over here and 2 over there. 1 or 2?
1. 2?
2. It's not a 3. I think I have an example I'll post on the web of 3. It's 2. Okay, so now before I pulled that BS of like ammonia and HCl being 1 to 1, so there's only 1. In this case, it seems like, well, these come from here. So this dictates those. Okay, chemically independent. Let's go back to the first problem. Sodium, 2 oxygens, 4 hydrogens, 2 hydrogens. It don't work. You see, it's very tempting because this is on the other side, but this does not actually fully describe both of them. It doesn't get this one. So you have to add in 1 more. Now, you can say that the other components, the 2 components are these 2, or these 2. It really doesn't matter. But it turns out that it is, in fact, C is equal to 3. Okay, again, I will post several examples on the web for you to get used to this. I'm not going to beat you over the head on this stuff because I consider it sucky. So let's do, hold on. C minus P plus 2, I have to remind myself, 3 minus 2 plus 2. Okay, 3 degrees of freedom, which would be same thing as like whatever its equilibrium is, which I control, temperature and pressure. And temperature and pressure, pressure, again, that's the chemical potential of this guy kicking in. So again, it makes sense. I can control temperature, what was in there, that's equilibrium. And as before, I've got a gas, and that means I probably need another degree of freedom. Its chemical potential is going to depend on the box it's put in, and I decided that. If I put it in a big box, if I put it in a little box, it will change the outcome. If I put it in a big enough box possible, the entire Earth, then the equilibrium is shifted completely towards here, because the gas will flow away, and it will never stop. So yeah, that's obvious I control that. So, anyway. So again, I'm just going to provide examples, a bunch more of examples, and have fun with them. And really, all right, we got to go in a new direction now. So this is always kind of an aside. That's one thing I don't like about this stuff. Again, it's just like, here it is, okay, goodbye, it's gone. This guy is more important. And let me tell you what the big picture is first. And let me tell you about some of the trickery I can pull on you. What we're going to be deriving in a phase diagram is, because of the nature of the mathematics involved, and I'll point out when it happens, I need to give you a point on a phase diagram. I will give you a triple point. And I will say, okay, here's the triple point. Tell me where the solid melts at a different temperature and pressure. Well, I'll say, what temperature does the solid melt at this pressure? Now, what you can do is build a line by those equations. I could have said, okay, here's the triple point. Tell me where the liquid evaporates. And again, you can calculate at this temperature, it's this pressure, at this temperature, it's this pressure. So you can build up these phase diagram lines point by point. I'm just going to ask for 1 point, obviously, but that's the idea. I can say, given this temperature, at what pressure, should label these, what pressure does the solid sublime to a gas? Again, point by point, we can build these up from nothing, except a starting point. You must have a starting point, otherwise this doesn't work. And again, the kind of thing you do in grad school is you figure out the equations that you solve all of this without the initial point. That's, again, the grad, what we do anyway. It's not for today. I mean, you need to learn how to do this before you do the grad school stuff, right? And the way we're going to do that again is, at these lines, the chemical potentials are equal. Oh, and I meant to actually tell you one thing before I do any more mathematical analyses. Again, it's a prerequisite that to be on the line, the chemical potentials have to be equal, but you can create things in a phase that is not in equilibrium. It's not easy. But have any of you ever overheated water in a really smooth bowl? Any of you ever done this? I see a couple of nods. What happened was I remember hearing screams from my kitchen when I was still in college. It was my mom. It scared the hell out of me. What happened was my mom had an exceptionally smooth coffee cup and was boiling water, and then did the normal thing on the microwave and opened it up. It's not boiling. What the hell? Oh, the microwave's broken. A spoon touches water. Kaboom. It instantly turned to gas. It scared the hell out of her. So you can actually be here, right? This is the gas, and actually still be in a liquid state. And that's because you have to have a nucleation event, which I'll explain a little bit more. You have to start making bubbles. For the liquid to boil, you need to have like a rough interface. You need to have a little nucleation spot, which is why coffee mugs actually should be a little bit rough. And without that, you can actually drive something that's here that's still a liquid. It's just not in equilibrium, and it can cause accidents. You actually really do need to be careful about that if you have really smooth cookware. Here's another thing. You can actually also, you can do the same thing. You can be like here in the solid phase and still have a liquid. And you can really do extreme things with this. The record, if I recall, if I remember correctly, is you can get liquid water down to minus 60 degrees, which is kind of extreme. I mean, for all of us who grew up in America, minus 60 is pretty freaking cold. I'm pretty damn certain water wants to be a solid. And the way they did it, the way it was explained to me, because I was there when it happened. I was actually there at Berkeley when they got this record, so that was kind of cool. I know the guy who did it, Kevin. He and I were classmates. What he did was he had a vacuum chamber and he had a nozzle with liquid in it, and to prevent that nucleation I told you, the rough spot, he shot the water into the vacuum chamber on its own, so it never touched anything. And basically how fast you made the liquid jet is how much it cooled. And there was a little evaporation as it shot through. And then he used x-rays to measure the structure of the water, and the structural signal was liquid state. When things turn from liquid to solid, x-rays can tell you that, and it's really obvious. And so he hit the record of 563.5 K. 560, not K, C, when he managed to keep that ultra-cold liquid It's still a liquid state, not a solid, so. Well, I thought that was a cool story. All right, anyway, so again, you can make things not equilibriums, but when I draw a phase diagram, I'm not gonna play those reindeer games. I'm gonna wait, I'm gonna poke things if I have to. You really do have to, so that I know where these lines really are at. Okay, so let's look at this. Change in chemical potential. Now, I'm not gonna play any more tricks with vacuum chambers or boxes. Again, we live in a constant temperature pressure world, so let's go back to delta G. So here's our standard change in G in the form of chemical potential, just because, why not? Okay, now what I want to do is look at every one of these independently. And this is going to allow me to derive, get the equations that derive these lines. Right? So if I can do this one, let's do temperature first. Okay, let's not forget that. Okay, now let's plug back in G. And now since we have a phase change, I do want to consider the number of moles changing. Right, a phase change. So I am actually transforming moles around. And this will be at constant P and T. And the dt is at constant P. Right, because this is the definition of chemical potential. And I'm asking for the change in chemical potential and temperature at constant pressure. That's why that's there. This doesn't matter. All right, what I'm going to do is I'm going to switch these. I'm going to use the Euler principle, right, of exactness. So I'm permuting the order of differentiation. And I remember well enough to know that this is actually, if this is delta G form, that is minus chemical, minus entropy. Okay, minus, just remember your delta G's, all those partials, right? They're coming back. Now here's a funny thing, I didn't go over this. There's a really neat thing that you can actually say this is equal to entropy per mole. Not the change in entropy, just the entropy per mole itself. So the reason is, again, I know that this is how much entropy changes with change of moles, and I'm telling you it's the same as the entropy per mole. The exact mathematics is because I can actually integrate them both because they're extensive. You cannot integrate temperature or pressure, that's kind of nonsense. But I can integrate things that are extensive to give myself S over N, which is entropy per mole, which we always have that little, remember that, the little M, that means per mole. Now, let me prove that real easy. 4 cats, 2 rooms. Entropy says there's 2 cats per room. I get rid of a room, I've got how many cats? 2 cats. How many cats do I have? 4. How many rooms? 2. 2 cats per room, same number, right? So, it makes sense if that's the case. So let me show you what that does. Because I'm going to run out of time. Got my board, this is terrible. Let's look at chemical potential. And let's look at temperature. Oh, sorry, minus. Sorry, that's really important. Okay, now at 0 degrees K, let's think about, I don't know, whatever, it's water, who cares? At 0 degrees K, I've got some chemical potential. I don't know what it is. But I know as I heat up the solid, that chemical potential is obviously going down, right? I can bring this over there, and I can see entropy is always a positive number, and it's changing, sure, but whatever. But it's always a positive number. I'm just going to draw this as a line. I don't think it really is a line, but I'm just going to do it that way. Okay, so chemical potential is going down with temperature. Now, what's got more entropy? This is the solid. What's got more entropy? A solid or a liquid? Obviously obviously a liquid, and there's no tricks there, all right? Okay, now, is the chemical potential of the solid greater or less than the liquid at lower temperatures? Now remember, the solid's there. The solid is there, and I'm asking, which has a lower chemical potential, the liquid or the solid at low temperatures, whether it's a solid? Well, basic, you've got to use this stuff, don't memorize equations, you got to know what they mean. Okay, what?
Solid.
If this, that's a good guess. At equilibrium, but we're not at equilibrium yet. We're trying to build the lines. Well, I got to know where they cross, right? All right, anyway. So again, if a material is in a solid state, that means its chemical potential was the lowest. It was the lowest, right? The material with the lowest chemical potential is always the winner, right? And remember, that energy goes downhill. All right, so that means I know that the liquid is actually up here. But the liquid is changing. It's getting lower at a faster rate. Is it? Yes. Now remember, everything's chemical potential goes down with temperature. I'm asking, I know that the liquid is up here somewhere, but does it slope harder? Yeah, because it has a greater entropy. Here's what's going to happen. I don't know how much higher it is, but it is higher. And now I've had a cross. Sorry. I've had a cross. This point, at whatever pressure that is my solid liquid line. So I've got the temperature, I have to define the pressure, which I'll do that in a second. But this point here, this temperature, whatever pressure that corresponds to, is 1 point on this line. Okay, now the gas, sorry, I should have done this. The gas has a lot of entropy, right? Right. Now this is some point on the liquid vapor line, somewhere, whatever temperature that is, and then we'll figure out how to calculate the pressure. And now I've got my point, and I just keep changing temperature and changing pressure, and I build this whole line up. So, yeah, there you go. This is why phases change. And don't forget, because you did seem to have forgotten, that the lower chemical potential phase is the one that dominates. And the points that they cross are obviously the equilibrium points, which are exactly the lines on this thing. Okay, next time I'm just going to go ahead and end here, because I'm already going to be a little late. We've got to do dU dP, and we're going to find that it's volume. And that allows us to choose the pressure. We will adjust pressure by changing it, and then we'll have P versus T, and then we can go back to function the line. Again, sorry I don't have your homework on Friday. You have till 5 to get me your homework, and I'll see you Friday.